at the Type CP relay. We're going to be doing a 10-minute relay review. Hope you enjoy it. We're going to get into some of the functions, features, and testing of the unit. Here's a look at the relay out of the case. It's important to note that we have AC and DC present on this relay. You'll notice the 6 tabs. You can see the DC on the left and the right with the A, B, and C phase input AC in the middle. Let's take a look at the settings and adjustment on this relay. We're going to take a look at the scale plate. That's going to determine where we place our 47 low voltage and our 59 high voltage pointers, which have contacts on the bottom of them. Here's a view of our ICS, or indicating contactor switch. It's set up on our low voltage side. You can see the tap points, the seal-in, and the target at the bottom. On to the inner workings of the relay, we can see the coil spring, its respective adjustment, the mobile contact, the high voltage and low voltage contacts, with the spring being the primary adjustment for the high voltage pickup. Located on the back of the relay, we can see the E-type laminated structure with the coil on each leg. Input into this relay is a delta connection, although a Y connection is formed by connecting one lead of each coil together. Let's take a look at what makes the induction disc turn.
The CP relay, we have our A phase winding, B phase winding, C phase winding. Now all of this, imagine this black dot is the core that's inside the magnetic laminated core, right?
E-type structure.
Yeah, so first let's talk about, like, let's say they had a common core all in one direction. Okay, A, B, and C phases all wound around the common core. So let's represent this. This graph is like a time graph. Common core meaning that they're all of their magnetic fluxes are going to be in the same material at the same time, right? So this is one time scale. This is the same core. So hence the arrow. What's going to end up happening is we take the area under the curve, which pretty much is the integral. So the amount of time that it takes let's try to break it down a little simpler than that. So let's say I wanted to measure the flux in the core at one specific time. So I'm going to take my black marker here. I'm going to say at time, I got to draw my green one in so I didn't extend it back that far. Okay. So let's say at time 1, I add up the total amount of flux within the core. Can anybody tell me what this plus this
0.
plus this is going to be? It's going to be 0. If I take that same time stamp anywhere,
0.
if I add them up anywhere, it's going to be 0. Because the amount of flux is going to be the same any place, and it's going to equal 0.
Visually, that's so
Visually,
confusing.
it adds up to 0, right? It has no choice. The outer flux outside of this core is going to be nothing at all times, as long as they have an equal time separation.
And time
Right.
separation.
Time separation and magnitude. If they're the same, which a balanced system would be, that's why we can't use just one core. So we separate it into 3 cores, and I say, okay, take that same timestamp. I say, at time 1, I go, okay, well, time 1, A phase flux is 0. Okay, no field flowing through A phase. Cool. B phase, okay, I have an increasing flux. Okay, I'll put that. At C phase, I have a very decreasing flux, so even more than my increasing on B phase. So that means at time 1, my flux field is actually moving between these 2 coils, right? Let's say at time equals 2. We'll do the same thing. So see, every time this field configuration, the flux is actually shifting between the 3 phases, but they're always going to produce a difference because they're on 3 different cores, instead of being on the same core where they all cancel out. Does that make sense?
Yeah.
Okay.
Visually, and should make it turn smoothly, they're all going to be equal at any point across the timeline.
Right, so magnitude-wise, so at this point, this is 0. This one's increasing, this one's decreasing. I've got a field, or I've got flux set up in this direction. Okay, so let's do time 2. So I got A phase is decreasing. Okay, I've got C phase is decreasing. And I've got C phase is increasing at the max almost. So I've got a field that's set up in at time 2. So comes out this way, goes down each core, comes back. Right?
Yep. A, B,
And it's
C.
that shaking flux that's gonna turn that disc. So again, it just has a path there.
We've got the
Yeah.
spatial separation
Yep.
and
Time
timing
separation. Yep.
And that's what will make the disc go around or
Boom.
not go around.
Or not. Right. So again, if you take all of the area under these curves at different times, it's gonna not be zero,
Yep.
right? It's gonna be always going to be in the direction to turn that disc. Cool. Work?
I like it.
Awesome.
Don't erase it.
It's a pretty drawing.
With your
Thank you, Captain, for a much better explanation than I could give. Here's the simple part. Here's the air gap, the induction disc, and the EMF that makes the disc go round. From the bottom of the relay, you can see the adjustable slug that's going to affect our magnetic field, which will increase or decrease the drag on the induction disc. The adjustment, if we turn it to the right, will increase time, to the left will decrease time. For our low voltage timing test. From the side view, we can see the drag magnet and also the set screw that you'll want to back out and put back in after making any adjustments. Here's another view of the contacts before we move into the schematic portion of this review. For our particular application, we use the ICS setup on the low voltage side. We do not use an IVS. And if you're following along in an ABB manual, it's page 3, figure number 4. Here we can see the 3-phase delta input, and at the top you can see the connection for each coil internally to the relay, turning it into a Y. Here's another shot of the front of the relay so we can see the connections before we move on to what's actually happening to the contacts at each point. Under healthy system conditions, our high voltage contact input is made up, which also acts as our LSR reset. As our healthy voltage decreases, all contacts will be in the open position. If voltage continues to drop, it will make up the low voltage contact. At that point, our ICS should operate, creating the seal-in and dropping the target. We'll be using the Manta 5100 in a delta configuration. You can use it in an open delta, but we'll be doing delta today. Remember that safety is first and foremost. Overvoltage pickup test, 3-phase sensing on 1 and 10. Let's go ahead and get started. For the overvoltage pickup test, we're going to want to find out our nominal voltage that's given on the setting sheet, calculate the acceptable range, which in our case is going to be plus or minus 3%, and then we're going to ramp up the voltage until the high voltage contact is made up, and we can see that on the screen there with the Manta for the inputs. Once that's made up, we can back off a little bit, ramp it back up, find out where the pickup point is, and record accordingly. For the undervoltage, we're going to move sensing to 2 and 10. Similar to the overvoltage pickup test, with the undervoltage pickup test, we're going to take the nominal value plus or minus 10%. We're going to bring the voltage above the low voltage pickup. We're going to back it off a little bit, bring it back up, once again back down. That way we know exactly where the low voltage pickup is going to be and then record our value. For the undervoltage timing test, we're looking at 3.7 seconds nominal, plus or minus 4%. What we're going to do, we're going to ramp the voltage up until it makes contact with the high voltage contact. We're going to drop all 3 phases to 0, and we're going to record the time that it takes to make up the low voltage contact. For the target test and seal-in, we're going to be pushing DC in 10 out 2 according to whatever your tap value is set at. Our nominal value is going to be whatever the tap is set at. We're looking at a range of minus 50% to positive 120%. So just as long as the ICS operates within that range, it's going to pass. I'll start at 50% tap value and ramp up until operation. I verify the seal-in by opening the low voltage circuit and also checking to make sure there's no arc. We will then ramp down the DC current to make sure that the seal-in drops out. This will complete our as found portion. Now we burnish our contacts, tighten any screws, and make any adjustments necessary before moving on to the as left.